After understanding why we need a Type 2 PL, we might want to know other system-level insights of the PLs in the frequency synthesis. For example, multiplying a 100 MHz reference clock to 8 GHz. In most cases, the multiplying factor over the divide ratio of feedback frequency divider is an integer number. But we might need to know why we need the multiplying factor to be a fractional number in some cases. Let's start with a typical integer PL in the most common Type 2 topology. Since the PFD tracks the rising edge time or phase between the reference clock and feedback divided down clock, the charge pump's path width and polarity will depend on the PFD output. Therefore, in the PL's lock state, the reference clock edge may be started earlier than the feedback clock, and then the reference clock edge may be started later than the feedback clock at the next reference cycle. In other words, the charge pump will pump slightly more charge into the loop filter to speed the VCO up, and then pour slightly less charge from the loop filter to slow the VCO down at the next reference cycle. Then, in every reference period, the VCO is slightly faster or slower than the target frequency. Do you see any dynamic issue with it? Think about the sampling images for 5 seconds. Bingo! Either the sampling rate of the PFD input phases or the VCO's update rate will be the reference clock rate, which puts an upper bound on the PL's operation bandwidth. Could you tell why would the PL's bandwidth has a stability concern? Because of the reference clock frequency? Let's think about a simple driving example I learned long time ago. If you are driving your car with a passenger who you talk to, it's likely that you like to pay attention to the road and look at the passenger at the same time. Is that possible? Yes, you could. For example, you look at the road and occasionally look at the passenger, and then look back at the road, and so forth. The question is how often you should look back at the road after looking at the passenger. Any ideas? Right, it depends. If the road is very straight, the direction adjustment that you steering a wheel in the road can be slow. Then you can spend lots of time looking at the passenger and not spend much time looking at the road. However, if you are driving on a mountain road curving all around, you must look at the road much more frequently after looking at the passenger. Otherwise, you will easily go over the end of the road and die. This is a good analogy to the PL's discrete time feedback system for the PL bandwidth and reference clock update rate. In summary, if we want to have a wider bandwidth of the PL, you must be updating the feedback system more often, which sets the minima reference clock rate. Below the minima required reference clock, the PL will be unstable. On the other hand, if you have a constrained reference clock frequency, you must design your PL bandwidth to be at least less than 1/10 is the rule of thumb of the reference clock frequency to make sure the PL can be stable. After understanding the stability requirement between the PL bandwidth and the reference clock frequency, do you prefer to have a higher or lower reference clock frequency? Correct. Again, it depends. To make the PL have a faster settling response, you might want to have a wider bandwidth PL along with a faster reference clock rate. Also, if your VCO has a poor phase noise, you might want to have a faster reference rate correction and high PL bandwidth to reduce the VCO noise contribution. But when do you need a low reference clock rate? Think about the output frequency image for 5 seconds. Right, you may need to have the target output frequency, which is N times F ref. Therefore, to make sure getting all the output frequencies you need, it's likely you need to reduce the reference frequency to have enough frequency resolution, such that the VCO output can cover all the frequencies you need, which is a trade-off with the PL's performance we mentioned above. Again, a lower reference frequency leads to a longer PL lag time and a higher PL output jitter. Hopefully, you can realize the integer N PL's limitation due to the fundamental trade-off between the resolution, bandwidth, and noise. If that's the case, how can we achieve the high frequency resolution, high bandwidth, and low noise PL at the same time? Correct. We need a Fractional-N PL. But how to implement an arbitrary Fractional-N divider? This doesn't seem doable, but having two integer divide ratio, n and n plus 1, and switching between them seems possible. For example, we can control the different number of VCO cycles, P and Q, divided by n and n plus 1, such that the effective Fractional-N divide ratio would be P plus Q divide P divide n plus Q divide n plus 1. In general, for a specific example, n equals 10, P equals 90, Q equals 11, then the effective n is 10.1. Therefore, to get the output 101 MHz, we can have the input frequency to be 10 MHz instead of 1 MHz for the minimum frequency resolution. Then the bandwidth of the PL can be 1 MHz instead of 100 kHz to minimize the ring oscillator's PL's lag time and output jitter at the same time. Unfortunately, toggling the divide ratio between n and n plus 1 periodically causes a periodic disturbance in the VCO control voltage. What happens and what should we do to mitigate it? Yes, the periodic divide ratio switching will cause the runtime phase error accumulation over n reference cycles, which is a relative crossing burst in the frequency domain, and could be worse than the reference burst in an integer N PL. So, to avoid the periodic switching, we could randomly toggle the divide ratio and then convert the spur into the noise. Unfortunately, the noise flow of the phase noise could be still too high to meet the jitter specifications. What can we do? Think about the shaping images. Bingo! we can try to shape the spectrum of a randomized noise. For example, move the noise energy to a higher frequencies, and then the PL's low-pass response will filter out the high-frequency noise. But how to implement the noise shaping in a high-pass response? Right, the most popular and effective way is to apply the sigma-delta modulator, which tackle the divide ratio between n and n plus 1, such that the average is equal to the fractional number. Then the correlation noise is the divide ratio is a high-pass shape, and then the low-pass filter by the PL's low-pass response. Therefore, as you can see, the total integrated noise below is reduced greatly. The integer n PL is simple and straightforward for most frequency synthesis applications, but the frequency resolution will be the reference clock frequency. Therefore, to generate more demand output frequencies, we must reduce the reference clock rate, which is the update rate in the discrete time system. Unfortunately, to ensure the PL can be stable, the PL bandwidth must be low enough, or at least 1/10 of the reference frequency. Then, the low bandwidth causes both the PL lag time to be longer and a higher output jitter from the VCO contribution. At this point, you may realize that the integer n PL has a fundamental limitation in some applications. Therefore, we must need another fractional PL to decouple output frequency step from the input reference frequency, such that a wider loop bandwidth and can be achieved to realize the fast PL settling, higher VCO, phase noise suppression, and last application of reference phase noise through much small value of multiplying factors. As far as I've known, there's no way we can implement an arbitrary fractional divider. Fortunately, having two integer divide ratio n and n plus 1 and switching between them could get the average value of the fraction, but periodically toggling the divide ratio between n and n plus 1, generating sidebands, even though we could toggle randomly to convert sidebands to noise. Total phase noise would be too high. So the most popular way is to apply a sigma-delta modulator to shape the spectrum of noise and move its frequency energy to a high frequencies, and the PL will filter out the high frequency noise. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. And please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.